Helium-3 is a gas ejected from the surface of the Sun and blown through space by solar winds. When it reaches the Earth, it's blocked by the atmosphere. But on the Moon, where there's nothing to block it, the gas is trapped by the lunar soil. Slowly, over billions of years, huge deposits have built up.
At first blush, using the most conservative figures for the amount of helium-3 that's in the soils of the Moon, what we call the regolith of the Moon, there's about 1 million tons. That's a lot of helium.
It will be enough to power the Earth for hundreds of years. It's what Kulczynski had been looking for all along.
It's only within the last few decades that we've ever thought about the Moon as being a large source of energy. In fact, it may be the Persian Gulf of the 21st century.
It seems preposterous, but Schmidt and Kulczynski have set up a company with the extraordinary idea of strip mining the Moon and transporting helium-3 as a liquefied gas 250,000 miles back to Earth.
That's the first part of that video, and we'll get to the second part in a second. But I want to show you some of the stuff they were talking about how it's converted to energy. Like I said, the processes of standard hydrogen fission is highly radioactive, produces all those neutrons, it's difficult to contain, so on and so forth. So they combine deuterium and helium-3, that makes for a better, cleaner reaction. They do that in a thing called a tokamak. I'll show you one of those in just a second. Not discussed in this video, and I'm not going to spend a ton of time on it here because it's a difficult process to understand all of, but know also that there's a potential for, as I said earlier, helium-3 reactions, which don't use deuterium at all, which would, again, reduce by order of magnitude the amount of dangerous neutrons or radioactive neutrons that were released as part of that process. And so they're combined, as I said, using a thing called a tokamak, which is one of these deals right here. It's a containment facility and an accelerator. In this tube area here, we accelerate the particles. The containment facility keeps it from being radioactive and nasty, right? And eventually that's how we can create the fusion energy. There's a couple problems with it right now. Not only just the neutron reaction that we were talking about, but also that the amount of energy that it takes to create the reaction that would be necessary looks like it would exceed the amount of energy that is released as a result, which is a problem that has to be overcome. And a lot of people think that helium-3 is sort of the key to unlocking that. So there's a higher output of energy for a lower input of energy going in. I just realized that anybody's looking at this all the time. That characteristic is in German, so I don't know what all those German pointy lines mean. The arrow just points to tokamak. So that's part of how that process kind of works. There's two big tokamaks that you'll probably hear a lot about. One is in the United States at the National Ignition Facility as part of our nuclear weapons program. It's fairly well guarded and sort of a separate part of the Los Alamos stuff. There's also the ITER project, which is another of the tokamaks used for the same sort of process. But you'll see all those. The abbreviation ITER or abbreviation NIF for National Ignition Facility are the two main tokamaks. There's a lot of that kind of stuff in the literature. So the question then is, if we think there's helium on the Moon, and we think that it's useful for energy production, then how do we start to get at it, right? And so that's the next part we're going to talk about here. And I got the second half of this little video, I think, is the beginning of this discussion. Also, that guy that was talking, Schmidt, former Senator Schmidt, you guys will read lots of cards by him. There's tons of cards by him in the starter pack. That guy's pretty on his game and one of the huge advocates of it overall. So if you're thinking about people who sort of push for helium-3 and have a lot to say about it, Harrison Schmidt is one of those guys. And he's from Texas, it turns out. So we're going to talk a little bit. Let's watch this bit of video here about how mining helium-3 might work, the feasibility of that, and we'll talk about the debate around it. Oh, you're kidding me. This little circle thing that's happening is not part of the video.
It's not a madman's dream to go to the Moon and access its resources. We've been there, we know how to do it, we can estimate the cost. That's not a madman's dream.
Yet even if it were possible to mine the moon, not everybody believes we should be looking at it as an object to be exploited.
Okay, Houston, as I stand out here in the wonders of the unknown and try to realize there's a fundamental truth to our nature. Man must explore it. And this is exploration at its greatest. Here we go.
Edgar Mitchell is a former test pilot who took a degree in engineering before spending nearly 3 days exploring the lunar surface in 1971.
Going to the moon, for me, was a powerful experience, a turning point. And the easiest way to say that is going to the moon caused me to see the bigger picture, put things in a larger perspective, and to see Earth and our civilization as just a tiny speck in the larger scheme of things.
Wish we had time to just stand here and look.
Mitchell's experience led him to draw almost exactly the opposite conclusion to Schmidt's.
There are those who believe that expanding outward and using the resources of the rest of our solar system are what we should do. And perhaps in due course we will have to do that. But first, we have to learn to live within our means here, to live within the resources that we have, instead of just saying, well, we can consume all we want, and then we'll go to the next planet, consume all of that, and the next planet, consume all of that.
Mitchell believes we are still profoundly ignorant about the moon. And in our rush to exploit it, we could destroy valuable scientific information.
Boy, that's really tough rock.
People will just barely scratch the surface of going to the moon.
I can move it, I can rock it.
We've only had 6 flights land in 6 different locations, and we've been there a few hours each time. So it's still not much more explored than it was before we started. Until we know what the moon is really all about, the idea of trying to commercialize it is, in my opinion, a misplaced idea.
It's not a view Schmidt has much time for.
Some people might say that it was immoral to benefit from the resources of the moon. I personally think it would be immoral not to have those resources available in the most timely way possible. And so I think the moral question is more on the other side.
The voice of caution may anyway be too late.
Russians represented here as smoking.
Nikolai Sevastianov is the boss of Russia's biggest rocket company, RSC Energia. The company has a long and successful history of putting men into space. Sevastianov has a reputation as a shrewd and effective businessman. His rockets regularly take crews to the International Space Station.
Thank goodness you are safe. Look after the station. Remember, it is the cornerstone of world manned spaceflight.
But Sevastianov wants to do more than take crews into low Earth orbit. He too has seen the potential of lunar helium-3.
Let me explain this to you in very personal terms. There's been a lot of criticism that helium-3 is a fantasy, that it's going nowhere. Once, when I came home and told my wife about all the criticism, she got out a book and showed me how people throughout history have laughed at new scientific ideas. I remember vividly how when gas was found in the Arctic Circle, skeptics said it would be far too expensive to build pipelines to bring it out. But historical experience has shown that if you set people a task, it will be solved.
Sebastianov wants to begin industrial-scale mining on the moon by 2020. That's the same timescale as the Americans. It could get very crowded, but the rewards might be enormous.
If we had gold bricks stacked up on the surface of the moon, we couldn't afford to bring it back. This material, at several $1 billion a ton, is what makes it all worthwhile. There is nothing that we know of in the solar system that is worthwhile going out to bring back to the Earth other than helium-3.
Helium-3 could become the new fuel of the 21st century. A source of fusion power that could provide an almost inexhaustible supply of clean, pollution-free energy.
A metric ton of helium-3 would supply about 1/6 of the energy needs today of the British Isles. It would supply 10 million people in a large modern city for a year. It would, over the long haul, replace, for electrical power production, not only fossil fuels, but would replace nuclear power as we now understand it, fission power. So there are really very few disadvantages other than it's tough to do.
If these men are right, whoever controls them might just control the world's energy supplies for hundreds of years to come. Yet the obstacles are formidable. Even when we've cracked fusion technology, we're looking at an energy source that requires mankind to live and work in the most dangerous and unknown environment we've ever encountered.
To be honest, I think it understates it just a little bit, even to how dangerous it is what we're talking about doing, mining the moon. I think the videos raise three questions that deserve a little bit further explanation. The first one is the feasibility of this in general. We're talking about using technologies that do not currently exist to do something that we've never attempted to do. I'm not talking down on the helium-3 affirmative or any of that. I've already that app. I think the app's a good app, but I think it's important that we understand contextually kind of what's going on. Currently, we don't have an operational spacecraft to get people back and forth to the moon with any set of reliability. There is no moon base there. The processes that we would use, they suggested strip mining would be one of the things we would do. Shaft mining is definitely possible. Superheating is another possibility. Are those technologies to make all that occur in a zero-G or low-G environment, or also experimental and down the road to say at the very least? And so the feasibility of it, while all the processes of it itself are individually feasible, the intersection of all of those things becomes pretty difficult, right? I mean, we're not quite to the point where we think we're going to send people up to the moon to start the mining process. And these pictures are just pictures of artist designs and concepts of ways that we might go about mining, and I'll talk a little bit more about mining techniques when we talk about asteroids, and the asteroid mining techniques are very similar to the ones that we might use on the moon. So one question is the debate about feasibility, and like I said, it depends on who you ask. Someone like Harrison Schmidt, who I said writes a lot of cards about this, definitely writes excellent evidence that it's feasible, and the time frame for that is usually somewhere between 20 to 50 years, to actually begin the process of bringing it back, which would require us most likely to liquefy the helium-3 and return and shuttle it back and forth to Earth. Although there were various other sets of proposals, some much more scientific than others, some more science fiction than others, that suggest that we could send it back via either laser, potentially refine the energy on the moon, basically build a toke box on the moon, and then return the energy through either microwaves or laser technology back to Earth. Again, those are even a little bit further out for sure. But those are some of the ideas for those things. The second thing that I think is interesting that the video talks about, and it uses a search term if you're curious about where you might start to find some cards about this, is the idea of the moon being the second Persian Gulf. Now, obviously, if there's enough resources there, as they're suggesting, for several generations of energy, of efficient and low-risk energy, at least